Hello and welcome to another video. In this video we're going to be working on climbing stairs. And this is going to be a fundamental DP problem, so we're going to go through it pretty in depth because this is definitely, like, if you're new to DP, this is definitely one that you should practice and you should be able to solve it in every way ideally. So in the problem you're climbing a staircase. It takes n steps to reach the top, and each time you can climb 1 or 2 steps. And how many ways can you climb to the top? So in this first example, n equals 2, so there are 2 ways. You can either go 1 and 1 or 2, and here n equals 3, so you can go 1, 1, 1, 1, 2, 2, and 1. And so this is going to keep building. So let's say n is 4, and we tried to get to 4. So let's kind of, basically at every single point, we have a choice, right? We can make 1 step or 2 steps. So let's walk through all the paths to get to n equals 4 from 0. So yeah, so let's actually make this a little bit thinner. So let's say we take 1 step here, we will be at 1. Or we can take, let's actually redo this. Okay, there we go. So n equals 4. Let's say we take 1 step, we'll be at 1, or 2 steps, we'll be at 2. Then once again, we have a choice. We can either take 1 step and we'll be at 2, or we could take 2 steps and we'll be at 3. Let's finish this side. So here we have 1 step, we can be at 3. 1 step, there's only one choice here, right? Here you can take 2 steps, so you'll be at 4, and then you're done. So this is 4 as well. Can't take 2 steps here. So here you can only take 1 step as well. So 1 like this. Here we can take 1 step to get to 3, and 2 steps to get to 4, and 1 more step to get to 4. So you can see that, like, you're doing a lot of repeated work. Like, look how many times we got to step 3. We got here once, twice, 3 times. We got to step 2 once, twice. So, and as you keep basically doing more stuff, you're going to get more and more and more repeated values. So this is just like a fundamental programming issue. Like, let's say you are calling a function with a parameter a bunch of times, the same parameter, right? What you're going to want to do is you're going to want to cache your result, meaning you're going to want to take your results from your function and store them. And then if you ever call the function with the same variable, you can say, oh, look, I have it already, so I can just return it. And so that's kind of what we're going to be doing here. Instead of actually recursing all the way, we can just solve for these one time. So once we get to 3, we'll solve it 1 time. And then anytime we get to 3 again, we'll say we've been here before. We don't need to recurse a billion levels deep because we've already done this problem. And that's kind of the idea behind dynamic programming. And in dynamic programming, the first thing you want to do is figure out the memoization solution to a problem. And so what that's going to be is pretty straightforward. So it's essentially recursion. Let's actually make this bigger. So recursion with caching. Meaning we're just going to have some kind of recursive function. And the way normal recursive function works is it has a base case and a recursive case. And so that's what we need to figure out. We need to figure out the base case and the recursive case, and then we just add caching to it, which I'll show you, and that's pretty easy. So what's the base case here? The base case, basically when you're counting for the number of ways to do something, is we are at n, right? So if we are on the stair we want, that's one way to it. That's like one way we got here. So in this case, you would want to return 1. Right? Now, in the memoization, which is like the recursion with caching, it's otherwise called memoization, so we can write that down as well. You also do have this case of, like, let's say you're at the second to last stair. Let's say we're at 1, and then we take 2 steps. We would actually, like, overpass our result. So we can have a base case where we go too far, and we can return 0, or we can just check for that. So in our case, we'll just have a base case of we go too far, return 0, right? Because that's an invalid state. So the way with these counting problems, you basically just return 1 whenever you have a success and 0 whenever you turn a failure. And you're going to add like all of these in a recursive case. So like I said, if you're at n equals 3 and you're trying to get to 4 and you take 2 steps, you'll now be at 5, which will be invalid. So that's another base case we can have. So these are the ones we're going to have. These are 2 base cases. Now what we need to do is have recursive cases. So in this problem, basically, you have two choices, and in most DP problems, you will have like a few choices. And if you want to count up all the different ways you can do something, and every choice is valid, you basically take the number of results from taking the first choice and the number of results of taking the second choice, and you add them together. So here, we're only going to have one recursive case, and that's basically just going to be add together, taking one step, and taking two steps recursion, right? And there's one more thing that you need in a DP problem, and that's a state. Like what's going to be your parameter, and this you want to try to minimize because for the time complexity and the space complexity and things like that, your time complexity is all the states multiplied by each other typically, if all the states are possible to get to. So we want to have the minimum amount of information that can still like help us solve this problem. And so the minimum amount of information we can use to solve this problem is just going to be having the index of where we're at. So that's all we need. So now we pretty much have everything we need. So we're going to have a recursive function. It's going to take in an index. And the base case will be if we are at n, or if we went too far, we will return appropriately. And the recursive case is just take together recursing one step and recursing two steps and add those together. And that's going to be the answer. So let's actually code that. So you're going to want to have a cache for memoization, like I said, because you want to make sure that you're not recursing the same problem multiple times. So you just make cache in whatever language. Then you're going to have a function. It's going to take an index. And if index equals n, we want to return 1. If index is greater than n, we want to return 0. And here we just want to cache this value. So we'll say cache index equals dp of index plus 1, right? One step and two steps. So, and then finally we want to return this value. So return cache index and return dp. And where do we start? We start at index 0. So we can run this. And this should be fine. Let's just see. Oh, we forgot. See, so this is we forgot to actually have our cache case, right? We forgot to check, have we seen this before? And we actually got a time limit exceeded. Because what happens is if you don't like get your values from cache, this is going to be super long, right? It's going to be a tree that's going to keep growing and growing and growing and growing. So we want to have the cache case. So if index in cache, let's just return that value. Okay, there we go. Now it's a lot faster. So now, next thing we can do is we can code up the bottom-up DP version of this. And the bottom-up DP version of this is instead of using a cache and a recursion, you just use an array. So basically what's going to happen, I don't think I have anything added here, so I'll just make it manually. I'll add stuff later. So basically we're going to have a base case. So we'll do this n equals 4 again. And I'm just going to draw this manually for now, and then next time I'll actually have stuff. So 4, 3, 2, 1, 0. There we go. It's a little screwed up, and I'll draw the indices. So here we go. So we know that at 4, this is 1, right? Whenever we get to 4, this is valid. This is like our base case. So that's kind of how the bottom-up DP works. You start out with the base case, and we can also add one more if we want to. So we can add another one and we can actually just draw this in. We know that at 5, it's 0, right? Because we went too far. So 0, 5. And now we can basically just work backwards. And for every number, we can just take, like we know from 3, the answer is how many different ways can you get there by taking one step? So you get to 4. And taking 2 steps, so you get to 5. So for 3, we're going to have 4 plus 5, right? These two results. We're going to have the DP of 4 and 5. This is a DP array. So it's just going to be 1 plus 0, which is 1. And then for 2, it's going to be the result of going to 3 and going to 4 added together, which is 2. Here it's going to be these two, which is 3. And here it's going to be these two, which is 5. So now this is basically if we start at 0, this is how many different ways we have to the end. So essentially we're just going backwards from the end. So you fill in the end states and then you just go backwards all the way to the start and then you return the start value. So we can code that as well. Pretty easy one. So we can just comment this out. So we can just say dp equals an array, and let's take a look at the length. So it needs to be length n plus 1, right? Because you see for n equals 5, we have 6 values. So dp equals, actually we probably need it to be more. Yeah, because n equals 4. So it actually will make it the array n plus 2. So we're going to make 0 times n plus 2. And then we're just going to have this base case here. So everything is going to be 0, but we need to initialize at index n to be 1. And then we can work backwards from there. So we'll say dp at index n equals 1. And we just loop backwards from every index below n to 0. So we can say for I in range n-1, like this. And we can say dpi equals dpi plus 1 plus dpi plus 2. And this is basically the same recursive case, except now we're working backwards, right? Because we're working backwards from a state we have. So that way, anytime we call something, we have these states afterwards available. We're no longer recursing. We're doing an iterative approach. And this is going to be time complexity and space complexity. It's going to be the same, but runtime will be faster because caching and like using a dictionary is just like more overhead, and array is going to be faster. So you're going to be able to see that. So now we just need to return dp of 0 here. And so this also works. So you do have to run it like a few times because this is like LeetCode stuff is inconsistent, but on average, it'll be faster than the memoization solution. Okay. So we have one more. Basically notice that for every single state, it only relies on the next two states, right? Like 3 only relies on 4 and 5. And 2 only relies on 3 and 4. And 1 only relies on 2 and 3. And 0 only relies on these 2. So if your state only relies on a few states ahead, you don't actually need this whole array. We can just start with 2 variables and then we can manually just use those. So what we can do is we can start with 2 variables. So these 2 base cases here, the out of bounds and the 1. So we can say like, let's have 2 variables. Maybe we can call this like 1 and, or what's a good name? I guess I'll just call it like first and last. So first is going to equal 1 and last will be 0. And now we're just going to take a variable and we're just going to loop backwards. So we're going to loop backwards 1, 2, 3, 4 times and just use these 2 variables and change their values. So what we can do is we can solve for this, right? So this is just first plus last because 3 relies on 4 and 5. So we can make a temp variable if that makes it easier, but I'm going to do it in place in Python. So we can make a temp variable here and it's going to be first plus last. So it'll be 1. Then we can rename last to be the old first. So now this becomes this. And now first can be this temp. And you can see like we basically got rid of this variable here. So now we're storing first and last again, and we can do the same thing here. So we can make a temp variable be both of these combined. So temp equals 2. Last becomes the old first. So this now becomes last. And now this is first. And we do it again. So temp equals first plus last 3. Last becomes the old first. And first comes over here. And finally one more time. So temp becomes 5. Last becomes the old first. And here we have this one. And so now we have these 2 variables, and basically now we can just return this first, right? So this first will be this value here. So we're just using 2 variables, and we still loop back the same exact amount of times, right? We still loop back 1, 2, 3, 4 times, so we can leave our loop in place. But now instead of an array, we just make 2 variables. So we can code that as well. So we can leave this loop in place and now just have these 2 variables. So we can say first last. So first is our base case. So first is going to be 1. Last is our out of bounds case, which is 0. And then this is all the same. And now we can just do this in place, but you can use a temp variable as well. So you can say first last equals. So first is going to be first plus last. And last is going to be the old first. Now we just return first. And there we go. And once again, you can run it a few times, but this should be on average faster than the memoization solution. And it should also be faster in space, but because this problem has like such small constraints, it's not super consistent. Once you actually get problems that are a little bit bigger, it's going to be a lot more consistent that your stuff will be performing better. But in theory, now we only have 2 variables, so our time complexity is still O of n. So our time complexity is O of n for the memoization, for the array, and for this, right? Because we're looping from basically n to 0. So our time complexity is the same, but now our space is O of 1 because we just have these 2 variables. So that's what we saved. So we went from O of n space with this memoization and the cache to O of 1 with this iterated bottom up. And this is going to be like the best one. Now for harder problems, this is harder to do, but definitely for like this one, this is good to practice. So yeah, let's talk about the time and the space. And like I said, the time will be O of n, space will be O of 1. And you can recognize that because even starting at this memoization solution, if we go back to it, you can see that your recursive case relies on only the next 1 or 2. And so whenever your recursive case always relies on the next 1 or 2, this is possible you can get rid of this dimension. Because if your item only relies on the next one, you can just go backwards from the base case and just store the like 1 item instead of storing the whole array. So hopefully this is helpful. And if it was, please like the video and subscribe to the channel. And I just got a new computer, so I'll have like better stuff in the future. So just kind of doing this one late because I was spending all day putting it together. But yeah, if it was helpful, please like the video and subscribe to the channel, and I'll see you in the next one. Thanks for watching.